per the discussion, we need to convert a 64 location memory for the 8 kilohertz into a compatible 32 location memory. And if you observe the odd frames, actually we have four 64 location memories for the odd frame alone. Similarly for the even frame alone. So we need to, when we convert, before we convert, actually we have total 8 memories are there for the odd and even frame. It means 4 memories for the odd and 4 memories for the even. So when we try to convert the samples by compatible 32 location memory, we need to store 4 samples in one memory. So total 0 to 3 in the RAM 10, then 4 to 7 RAM 11, 8 to 11 in RAM 20, 12 to 15 in RAM 21. So similarly, it will keep on go as like the before thing till 159. So once 159 complete, it will start storing the 0 in the right side column of U3, and it will keep on started storing. Similarly, the sample of 80, it will start storing from the even frame with this location. So whenever a forward direction is there for any even or odd, it will follow this structure, and whenever a backward direction is there for an even frame or odd frame, it will follow this structure. So if you observe what is the writing address for the RAM, in the sense, we can clearly see here, it was 0th sample, writing address is 0, first sample it's 1, second sample 2, third sample is 3, and for the fourth sample, actually the address location is 0 in the RAM 11, then 1 in RAM 11, and 2 in RAM 12, and then it will keep on continue. So address 0 to 3, it should be copied, or it should be continued for 4 times in the RAM 10 to 1, and then 4 to 7. It means each 4 count has to continue 4 times in a RAM for copying the, or for writing the data in the RAM. So after writing till 159, again it has to start with the backward direction. So for the backward direction, the address is 28 to 31, and then 24 to 27. Again it has to start with 0 to 3, and so on. So this is for the forward direction, and this is for the backward direction right address. So once a write address is finished, we need to go for a reading. So when we want to read the data, as we discussed before, 0th sample has to read with 128, then 60th sample has to read with 144. So the address 0 and the address of 4, which is actually mentioned here. So address 0 and then address 4, address 8, 12, 16, 20, 24, 28. This is the order we need it for the reading address, which was mentioned here. So 0, 4, 16, 20, 8, and 12. So actually what it's representing in the sense, once we read 0 and 0, and then 4 and 4, after that 8 with 28 we have to read. So that's what, if you observe the reading address in this, if you observe the reading address is 28 for the for the right side RAMs. So 28 and then 24 and then 8, 0, 4. So this is the order we required for the input RAM. So once the input RAM is finished for the framing and windowing with the write operation, and for the FFT operation, reading operation is supported to read the different values as per the butterfly structure. So we'll move on to the slide again. So the read scan path now for the RAM 1 to 8 and RAM for the 1, 5, 9 to 6, 10. That means odd of odd and even of odd frames are forward direction. Similarly for odd of even and even of even is the backward direction. So the right scan chain, if you observe, it will be the vertical downward direction for the odd of odd and even of odd, and vertical downward direction from the even of odd and even of even and odd of even from the right hand side column. So once the FFT computation is finished, so to do the FFT computation, the samples should be in the required order. Samples should be read from the required order. So to read it from the required order, this scan path for read and write is used. So we need to generate an address based on this scan path for the FFT application. Next, we need to move on to the energy computation, which is S of n calculation. So for the S of n calculation, whatever the FFT coefficients are there, with that coefficient, we need to read the Milbank values. So as we discussed before, the non-zero coefficients for the 8 kilohertz and for the 16 kilohertz are mentioned in the feature extraction engine and input coefficient ranges as a table. So if we observe here, we have 240 samples as a non-zero coefficients for the 8 kilohertz and 477 samples in the 16 kilohertz. So still we need to reduce this. The reason, till FFT, each frame is evaluated for the 64 clock cycle plus 16 clock cycle as a control signal of enable, reset and read and write enabled signals. So we need to complete this S of n calculation also within 80 clock cycle. So the pipelining or the latency of each path will maintain close to each other. So between 64 to 80, we need to fix or we need to complete this operation. To complete this operation for the 8 kilohertz out of 239, either we have to read it for 4 values per clock, or else we can move it, that means for the Milbank values we need to read 4 values per clock, or else 2 values of FFT coefficients in the second stage FFT output RAM. So in this case, if you observe, when we read the sample 0, the input range, the coefficient 0 will be read, Mel coefficient 0 will be read. But when we read the coefficient of 1, the first bank first coefficient and second, first bank second coefficient, second bank first coefficient will be read. So this will be mentioned again. So this can be understood with by observing the 0th bank first coefficient. 0th bank first coefficient is 0 and first bank first coefficient is 1. So when we read the FFT 0th coefficient, X of capital X of 0, we will read only a 0th coefficient in the Milbank. So when we read the first coefficient X of 1 from the FFT, we need to read 0th bank first coefficient. That means the first location, second address location of coefficient RAM, and second and 3 plus 1, fourth coefficient or fourth location we need to read it. So in this again the same problem arises. If a single port RAM is there, either we can read or write a single value. So 0th location and 4th location, which is stored in the same RAM, we can't read it. So again, for the coefficient RAM, we are going to keep 4 different RAMs anyway to store 240. So after keeping this, as like the scan chain path, 0 to 64, 0 to 32 will be stored in the first RAM, 32 to 63 will be stored in the second RAM, and 64 to 96 will be stored in the third RAM, and 96 to 128 will be stored in the fourth. So it will keep on go till 240. So we can able to access different RAMs for the computation of 4 different MEL coefficients and 2 different FFT coefficients for the computation. So in that case, again, this stage will optimize within 64 clock cycle. It means exact 64 clock cycle for the 8 kilohertz. and 128 clock cycle for the 16 kilohertz. Since we are reading 2 coefficients in the X of n and 4 coefficients in the mill bank, we need to process for the S of n with 2 max. So 1 mac will do at the first filter bank, and the second mac actually we need to start with 63rd coefficient. That means the n by 2 position of the X of n, which is 63. So sorry, 64, which is there in the 16th mill filter bank. So when first filter bank start operation, same time 16th filter bank will start operation. It means, so half of the frame is we are trying to process it. So 64 values from 16 to 20, 5 banks, and 64 values from 0 bank to 15 bank or non-zero coefficients in the mill bank. So 15 bank computation time and 5 bank computation time is divided as 2 separate process. So 5 bank computation will happen with 1 mac, and the other 15 bank computation will done with another mac parallelly. So for doing this 2 different mac operation, we need 2 X of n and 4 mill coefficients, as we said again. So to do this, again we need 2 address ranges. So the first address and second address, whatever we explained before, as per the input RAM, the same order is followed for the